As promised last time, today is gonna be a bit longer, I assume, and what I have in mind is demonstrating a very magical data structure that you're probably gonna use a lot, or at least data structures very similar to this. And we're gonna do so by first introducing the basic concept, then make a massive optimization on it, the very magical one, and then some other optimizations that are also really cool actually. Not my idea, by the way, just everything I'm gonna show you today, oh, that was microphone, I learned myself by looking at code, and it's one of my favorite pieces of code ever. Like the whole idea behind it and the different optimizations. I love this data structure and the way it's implemented in some languages. And depending on how much time has passed, we're gonna make some further changes to the data structure to create a second one. Very similar, but very different usage. Without further ado, let's create a new structure. And the first one is just gonna use some existing data structures you've seen already, just so you can see what we actually use it for. And please don't spoil yourself by looking at the title, which we've already done because of me saying so. Create a new class, we call it a set. It's gonna be a generic. This class is gonna hold values for us, and I'm gonna be very lazy and I'm just gonna internally use a list data structure we've already seen before now. And this is gonna hold the data for us, and we're just gonna interact with the data in the list just as a prototype. Keep in mind, this is not how everything is implemented, or at least not how it should be implemented. This is just very straightforward way to do this. And yeah, public set. Just creating new list like that, and that's enough for the constructor. And now the important bits. There are three methods we're interested in right now. Three very important methods. One we call add to receive an item. I'm gonna leave that empty for now. Another one, yeah, that's right, it's called remove. Gonna leave that empty as well for now. And the last one, public bool contains, which also receives an item. Also gonna leave empty for now. And these three methods are all we care about, at least for today. And everything else we might add to the data structure will in some way, shape or form rely on one or more of these methods beneath. And what do we use this for? Well, let's create a new set, let's say for strings. Set, new set. Like so. And the way we would use it is we could add string, for example, maybe C. And this would give us a boolean. Was added, of course without a space in between. And unlike the data structures we had before, this one does not care about the order in which we add items. Let's make a second one, was added. 1, 2, 3, different one. So I've added first ABC and then 1, 2, 3, two different strings. And actually let's add another one because that's important that it works too. Just gonna add null, which is a valid value we can add, so far at least. This is the third one. So we add three different values, in this case the absence of a value, which we treat as a value nonetheless. And the order in which we add it is getting lost. So at least for our data structure as we create it later on, this information 1 ABC, 2 1 2 3 3 null is gone. At this point in the code we do not know anymore in which order we've added them, and we do not care about that. We do, however, care about knowing that it was added at all. what we expect is that these 3 calls will all return true, because in every single case we added a value that didn't exist in that set before. If I were to copy this, I'm very lazy with the names, I'm just gonna add numbers to everything, would expect that this returns a false, because ABC already exists in the set because of this command above. We do not add it a second time. In a data structure like list or any of the others we learned last time, or no, before last time, like queues and stacks, we can add an item several times and it will be preserved several times in there. But for a set, the item can only be added once. We can try to add it again, and that's not an error. It will just not do anything inside the structure. It will not change anything. The state of the data structure will be the exact same as before. The only difference is that we get a different Boolean back now that can be used to determine, hey, is this a new value or was it already in there? And that's useful because otherwise you would have to rely on the contains. And that would tell us for the DEF, it's not in there. But if I try 1, 2, 3, it should return a true because it is in there. Contains pretty simple. Is the value inside the data structure, yes or no? And lastly, we need a way to remove data from there. And since we don't pop anything off or dequeue anything or just remove anything, we have the specific command remove, which gets the value itself that we want to remove. So we don't have a positional data value that we can use, like an index or just knowing it was the 6th item. We have to know the exact value and we have an option to remove it. And that will also tell us a value, true or false, or give us a value true or false, tell us if the item was successfully removed because it was in there, or if it was not successfully removed, which means it was not in there. So ABC, this should be a true because at this point ABC is definitely in the set, so it should be removed. We do DEF, one that is definitely not in there, which we checked before. This should return a false. And actually if we do ABC a second time, it should also result in a false because after this line, ABC isn't in there. Again, we've only added it once. The second add doesn't add it a second time. So once we remove it, it's gone completely. It's not we remove one instance of ABC, we remove the entire value ABC from the set. So in a set, we only care about the knowledge, does something exist inside the set or not? We don't care about the order, the timing in which different values were added. We don't care how often it was added. We only care about, does it exist? Yes. Does it not exist? That's all we care about. Very simple idea, but allows us to do a lot of cool things. So for example, imagine you have a long list. I mean, this is not the best way to use it, but it's one of the many things you can use it for. So let's say we have a list of strings. A, B, C, B, D, like that. Let's say I wanted to know if there is a value at least twice in the list. Maybe I want to get all the values of this array that exist more than once. The straightforward way would be, okay, I am checking the first index in the list, in the array here, and just compare to everything else in the array and see it doesn't exist. And then I check the second item compared to anything else on the right, because the comparison with the first already happened. So I compare B to C, B, and D, and I would know, oh, yeah, B is in here at least once. Okay, cool. And then I would check C, and then B again, and then D. And there's a lot of comparisons in here, but it works. And for a small array like here, that actually not that bad in terms of performance. With a set, however, I could just go through the entire list for each string. Yes, yeah, let's do it like that. And let's leave the code above for now, just as an example here though. So if this returns true, yeah, let's do like this. Yes, lists more than once. Let's remove the brackets to make it more concise. And that's it. We just add the value. If it's the first time we've added it, oh wait, I have the wrong way around. Okay, forgot the not. So if it's the first time we add it, this add will return true because we've successfully added it to the set. And so not true is false, and so this if is ignored. Next item. But if we add a certain value a second time, this add will return false because we didn't add it to the set anymore. It was already present in the set. And in that case, not false is true. This if will trigger and we will output that value. Simple example of where a hash set, now use the name as well, okay, the title name, where a set in general is useful, checking for duplicates. Maybe you don't care about all the values you presented, maybe you only care about the unique values. Maybe you also just want to know what are the unique values in this entire array. And having the set is a useful filter for that. There are of course other methods you can use to find duplicates, but that depends on the exact data you have in front of you. Some methods work, some methods don't. For a string array, the set is, I almost said it again, the set is one of the better ways for smaller amounts of data. Sets have limits. They also take processing time and resources, so they are not the cure-all for everything, but they are in general a good solution that will get your program running. So let's leave the code as is. We just want to write something that will successfully run all of this. That means we have to implement the methods. And again, this is just a prototype to show what the set in general is doing. Let's go through the different methods here step by step, starting with contains because it's the easiest one. And actually, we can use this code as is. List itself, the default type, provides us with a couple of interesting methods we can use already. And they already include the 3 we have right now, but they work slightly different. Now, contains is just straightforward. I'm giving it an item. Is that an item? And it will check if that item is in there. And we can do that manually as well. So for each, go through the lists. TI. Okay, we go through the entire list we have with a simple loop, and we just check if I equals item. Alright, we can't do that because it's a generic, so we use the equals. If item and I are equal, return true, and if not, return false. This would be the more manual approach. We could even split this up further by using a for loop with just an iterator, or we can do what we learned last time and get the IEnumerable feature of list and just get the IEnumerator, go through it manually. To make our life easier, we're just gonna do this one. Takes less code. So for this simple implementation, this would be the job. And remove would actually do something very similar. Though we cannot rely on the existing remove. Oh, did they? Okay, I wasn't aware that it also returns a value. In that case, we can use it. Let's just check if it's the right one. Okay. Nope, it's the right behavior. That's the same behavior we expect from our remove. I thought that remove didn't have a return value. Somewhere in my mind it was a void method. So either that was a later change or I think of something else, right? Well, that's good to know anyway. The add, however, is something we have to change because list does have an add method that works, no problem. This one is definitely a void. Yeah. Because a list can have the same item multiple times, there's no reason to check if the item existed beforehand. So we need to check that ourselves, and we can use our own contains method for that. So if item is contained, return false, otherwise added and return true. So this emulates, or not only emulates, this is the correct behavior for our set. And we did most of that on the back of the existing methods in the predefined class list. And this isn't the best way to handle that, but it's a way we get the behavior, and we can now use this code and check it. If we did anything right, or if we did anything wrong, let's just run it. Something we can do in the debugger now. Once I step through a method, we can immediately see the values for the return values from the different method calls and what is stored in the different variables. So right now we are in this line, the highlighted one. I'm pressing a button and we're just advancing by one instruction. And the return value for, oh, can you see my cursor? Yeah, you can see it. So you can see here the set method, the add method of set returned to true, and that was stored in added, which is also now true. So that worked. We added ABC, and that returned a true because it was newly added to the set. Great. The same should happen with the 1, 2, 3, and with the null. And you can still see the variable values here for all three true. Great, that's what we wanted. Now ABC at this point is already in the set, so this one should return false. And it did. Great, that works. And this contains now should also return false because we never added def. Correct. This one should return true since we've added 1, 2, 3 up here. Correct. Remove ABC, well, it's in there, we should get a true. Correct. Def was not in there, we should get a false. Correct. And ABC was already removed, so this should also return false now. Okay, and now let's just execute the rest of the code. B exists more than once. That is correct. It's the only string in this array that exists twice. So code works, our set does its job, and you could actually leave it as is and do your own thing. So if you're writing a larger program and you need a certain behavior and there's nothing that already does it, you can whip up your own class, your own implementation of class or struct or structure or whatever you need to just get the right behavior, even if it's not optimal. Like, this is not a very good way to handle this. One, because there are already structures that do this thing, of course, but also because it's poorly optimized. Perfectly though for just prototyping. Just get your program running and see if it works at all and if it's worth expanding on this class at all. Maybe you don't need it after all. Maybe you find a better way to handle duplicates on a string array and you don't need the entire class anymore. So prototyping, just do something like this. Simple, stupid, it works. Great. Good for testing the logic of your program. But performance-wise, this is a nightmare. Well, okay, nightmare is a bit of an exaggeration. A lot of an exaggeration, actually. Sorry. To drink something in between. Gonna talk a lot today. The basic performance of a list is not bad. Especially if we just add a couple of items. we have to increase the array, but dynamic arrays can actually be implemented fairly efficiently after a while, so that's fine, I guess. Contains is a different story though. To check if the item is in there, think of the manual implementation we did before with the for each. We have to check every single item in our list. Everything we've added so far has to be compared with our current item, until we find either a match, at which point we can abort early and know we don't have to look anymore, we found it, or we didn't find it and have to iterate through the entire list, only to come out with the conclusion that it's not there. And well, that doesn't sound too bad. We just go through a list of a few items. Once you have a couple thousand or tens of thousands of entries, or maybe millions, that's gonna take a long time to process, especially because comparing to values isn't always that easy. Just comparing to integer values, is a 1 equal to a 2? That's easy. That's even built into the hardware, computer hardware. The CPU can do that like that. Instant. Almost. But if you have complex classes and items, data types, then the comparison can actually be quite intensive. It can be actually quite an ordeal to process all the information in one piece of data and compare it to every single piece of information from another. So comparing every item, not ideal. It gets worse even with the remove. I mean, we have to of course mention that this contains has to be run for every add beforehand, so technically add is bad. The actual adding of the item isn't so bad, but the contains method before is. Remove is maybe the worst offender so far, because we might have to iterate through the entire list first, just to determine if it's in there at all. And if it's not in there, we can at least stop at that point. We've only wasted the same amount of time as it contains. If we do find it, however, we can abort the search early, but now we have to remove an item from a list. And lists are backed by an array where every item has to be right next to another inside our memory. So if we remove one in the middle, we have to then, let me draw something for you. So that doesn't look good. Let's try again. Actually, wait, there was a new feature. Let me try that. Haha, that works. Cool. So 1, 2, 3, 4, 5, 6, 7. Well, doesn't need to look good to work. So let's say these are the different items in our list. The list might itself be longer, that doesn't really matter right now. So there might be 3 spots on the right. We only care about these ones in the first 7 places. If I remove the 3, for example, I can't just leave this spot empty. No. I have to remove the 3 and then copy the 4 over to fill the gap. Then I have to remove the 4 by copying over the 5. And copy over the 6 to overwrite the 5, and then copy over the 7, overwriting the 6. And then the last spot becomes a free spot for the next value. I have to do that for every removal. I have to, in the best case, not do anything at all because I'm deleting the last item, in which case, okay, it's free, nothing to do. In the worst case, I have to remove the very first one, which means I have to move over every single value in my lists. So either I'm first looking through the entire sequence here to find out that my value isn't contained at all, or I may get to abort early because I find it, but then I have to suddenly copy over all the other values on its right anyway, which is still processor heavy, but still a lot of memory management because I have to copy all the values and it still has to iterate through all the values. The CPU can do some clever things nowadays, where the underlying hardware can quickly shift over some data in the memory, but from a purely theoretical standpoint, removing items in a list is still not ideal. So instead of a normal list, what we might prefer to do is using a linked list. Because a linked list, so let's go up the demonstration again. The linked list, I would have 1, 2, 3, 4, maybe 5 tall. Yep, that's up the tier. 6 down here. 7. And they just point to one another in different points of our memory. And while I still have to iterate through all the different entries to check them all one by one, at least in this case, the removal is pretty easy because I just have to, for example, for the 3, just drop this connection and have the 2 point directly to the 4. So the 3 itself is technically still in memory. That's something for the garbage collection to take care of. But as far as our program is concerned, this is gone with the wind. Belongs to the ether now. And at that point we can stop early, just like the contains. So a linked list is preferable in cases like this where we expect data to change quite a bit. And with a set, maybe you will just add things, that's fine. But if you expect things to be added and removed and then maybe more getting added, the more removal you have, the more you have to change the set constantly, the more you gain by having a linked list. Of course, having a linked list itself brings some issues. Said it earlier. With a linked list, we have to go through every single item one by one. Which we did so in the list or array version as well, so that's not that much different, right? Why is the linked list so bad? Well, think of optimization here. Our contains method has to go through all these different items to find the one matching. And the add method uses the contains basically, and the remove also essentially does the same thing as the contains. They all have to first iterate through every single item to compare it to whatever item you're given. To speed this up, there are a couple of methods which usually involve sorting the entire list here a bit. If you look at the top right now, the numbers, assuming we just store integer values and not strings, let's assume I'm storing integers, they're all in an order. So if I had still the array version or the list version, where everything is neatly aligned and accessible through the indices, I could just check a value, determine that this value is way bigger than what I'm actually trying to compare it to, so everything on its right is out. Don't have to compare it anymore. Everything on its left is smaller, so it has to be somewhere in here. And then maybe I should compare it to the 2. Decide the 2 is smaller, so it has to be on the right of the 2, but on the left of the 5. And right here, that's only the 4 now. This whole concept is usually framed in binary search. If you look for a specific term to look up for that, we probably have to talk about search algorithms and sorting at some point, though I'm hesitant to do so because it's really boring, honestly. Some of that stuff is really confusing only, useful, and you rarely have to implement something like that yourself. Admittedly, binary search you might have to implement some cases for specific data structures, but at least sorting isn't something you write yourself. Usually, Have I ever? There was one instance where I had to implement the sorting algorithm myself. One, for a very, very specific case. And even then it wasn't a traditional sorting algorithm, more like a cheat version because, look, doesn't matter. Anyway, if the entire list is sorted, we can take shortcuts by peeking ahead and comparing values instead of going one by one by one by one. This peeking ahead gives us an advantage in that case. But that only works if we can peek ahead. And of course that only works if the data can be easily categorized as this is less than or greater than, which for strings can be actually done, but not for every piece of data it's easy to frame greater or bigger. For number, trivial. For a string, still possible. Not everything will work with that, and we right now try to implement something that works with any data type. That's what we have generic. But this peeking ahead is the actual issue we have to focus on right now. We have a linked list now to get more optimal memory usage, just to make it quicker to remove data mostly. But because it's a linked list, we don't have an easy way to peek ahead. We can see the very first item maybe, but we don't know where this position for the 4 is. To find out where we can find the 4, the now third item, we have to first go to the second item, and then we know where the third one is. We cannot jump directly ahead. All these positions are a mystery to us in a linked list. So we have to find a way to make this whole process of finding data more efficient, despite not being able to sort the list and despite having issues with peeking ahead. What can we do in that case? Let me phrase the problem again, maybe differently. I have a couple of values. They're all arranged in a list. And maybe it's a linked list, maybe it's a normal list. Let's just assume you don't have an easy way to find a value in here. It's completely unorganized. It's a long list and you can only go in this list from one item to the next, piece by piece by piece. And you still want to somehow speed up finding a very specific item in this list. What can we do? Let me give you a hint. What if, regardless of what data type we actually use, we find a way to get a certain property for these items? Let's say for the start we get a certain property that sometimes is true and sometimes it's false. As simple as that. We can verify a certain property of any piece of data that will give us either true or false. And we assume that it's roughly 50-50 which one is gonna be. How could that help us? I have a mystery function that will return a true or false, depending on what value I feed it into it. So each of these will give us either true or false, and it's roughly 50-50 which one we get. How could we use that to our advantage? Okay, don't see any answers, so let me give you a demonstration. Let's say this one is true, this one is true, this one is false, 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 this one is true. Like, these are somewhat random now, right? Don't try to figure out the pattern here, they are random. Well, these properties can help us if we just introduce two different lists. If we look at just the ones that are true, we have 5, 0, and how many zeros do I have in here actually? 5, okay. Let's write them a bit closer. So 1,000,001. And for the false, we had 1, 3, -1. And now the screen share just stopped. Why? Did I hit a button somewhere? There we go. We're back. Okay. Two different values, depending on what input we give. And if we sort them by just this one property, we get two different lists with only 3 items each, instead of one list with 6 items. Nothing says that our set internally has to store everything in one single data structure. There's no reason to force us to use one list, for example, in our code right here. We could have a second list. List 2. And when we add an item, we could just... No, it's my private static bool pack t item. And when we do something, we could always just check the item, see if it's true or false, and depending on if it's true or false, we work with list or we work with list 2. Depending on the properties of our item, we choose one of 2 different lists. And that is helpful because with just one property, true or false, we've already halved the potential candidates. Before, we might have a worst case of filtering through 6 different items. Now scale that up to a large set, maybe that's 6 million items. But this true or false now lets us decide between one of 2 lists, which each have only roughly 3 million items, ideally. Of course, there can be scenarios where it's not as evenly, what's the term, distributed. But ideally, we find a way to get a property that's roughly 50-50, and so those 2 lists would be only 3 million each, or 3 in our case right now. And that means in the worst case, we only have to check 3 items. And now, let's imagine our simple check method does not only return a boolean, but maybe a number from 1 to 4. 1, 3, 4, 1, 1, 2. So right now we have a not so great situation with the 1, because that's 5, 3, and -1. Not so great. 2, there's only the 1,000,001. For 3, we have only 0. For 4, we have only 1. Now we have 4 different lists. So the worst case scenario is we feed it an item that also shares the property of 1. In which case we have 3 items we need to compare. Worst case. But in all other cases, it will be one of the 3 other properties which only have 1 value each. And we can directly compare with only 1 item, and we're done. Let's go a step further. Maybe it's not just 4 values. Maybe we only don't have just 2 bits to work with, but maybe 3 bits. Now we have 8 different values. So maybe 0. Oh, let's just use 1 to 8. So maybe it was 1, 2, 8, 7, 5, and 6. And I'm not going to write this out, but no matter what item we try to compare to now, there's only going to be one item that we actually have to compare it with, because each of the values on our list corresponds to exactly one value in our check method, in our specific property we want to compare it with. And if we're lucky, the item we're trying to insert or check for in our entire list here doesn't correspond to any of these 6 values, in which case we know immediately there is none. We don't even have to do a single comparison. So the basic trick is we don't use a single long list, we split it up into many different smaller lists. In each of these small lists we still have to compare all the items, and so we try to make as many lists as possible. But that means we need some way to get this mystery property, to get somehow a single value that we can generate based on an input that will be the same for some values, but different for others. And ideally, it's a value that's roughly evenly distributed across all kinds of values we can feed it into, which is a difficult task. That doesn't really work out as ideally as it should in most cases, but in reality, the systems we use are actually quite clever. There's a math involved that I don't even try to wrap my head around. I'm going to mention some of it later, but the basic property we're looking for that's commonly used, that's not to say that you can't do anything else yourself, right? Just to mention that, but the common thing used is a hash. Our check method is generating a hash. It's a hash function. And a hash is essentially a way to grab a piece of data, a small piece of data, a very large piece of data, whatever you have, and based on this unique set of data, you create a very specific, well, number. Let's put it that simple. And a change in the original data should usually also include a change in your generated hash. So a hash, an example for a hash that you're probably familiar with for large numbers would be, what's the English term? Quersummer. The accumulated sum, the shared sum. It's if you add up all the digits in your number. So 5, 0, 1, 3, let's just do positive 1, and then here would be 2. That's an example of a hash function you're familiar with. And that's actually giving us quite decent result already. We have 1 and -1 that give us the same value right now, so the list that gets the 1 is gonna be filled with 2 items now, but the others are just gonna have 1 item. And you can imagine now this applying to other numbers as well gives us a roughly evenly different distribution. There are only 10 possible values, at least if we get it down to the absolute minimum, if we try to repeat the entire process on each result until we get a single digit. That leaves us with only 10 possible numbers that all real numbers have to fit into. So there will be a lot of cases where the same hash will be coming from these from different inputs. That's just normal. If I have thousands of possible values I have to hash and I only have a handful of possible hash values, well, yeah, there will be a lot of overlaps. Pigeonhole in principle and all that. So We cannot avoid conflicts where several different values have the same hash value, and we have to deal with that. And there's no ideal way to solve that issue other than finding a better hash that has less collisions, is what we'll call that. Or by just allowing more hash variety. That makes sense. Either you find hash function that just inherently generates more diverse values for your specific data set. That means you have to look at what data do you actually want to use in your set, or what data are you working with in general, and find a hash function that can generate very good values for that specific subset of data you're working with. Optimize it for just that specific area. And collisions with all the other values that you're not working with usually don't matter. Or you just add more possibility for more hash values and that way reduce the number of collisions. So it isn't optimal, but it's a very simple way we can drastically reduce the performance cost. We just create a huge amount of lists we can store data into. So instead of just one or two, we might have an entire array, for example, of lists. And we might get an int from here. Let's recall it to get hash. And this int would tell us which of these lists we should look into. So before we do anything, we would get the, okay, let's use contains as is. And on here we would get hash of item. This is an index, and then we can do lists, list index, something like that. Generate a hash, and based on the hash, we find the list we have to check for, and that list is what we use. And we can do that for a lot of things. We can do that here as well. Like that. We have to initialize the list differently, however, of course, but that's the basic idea. We get the hash, based on the hash, we figure out which list to use. Now, the initialization is actually tricky because right now, list index could be anything. It's a full integer, right? And a hash, unless we limit its range, could be anything, really. And if we return an int, we should expect that anything might get returned in here. Any value an int can have. And not every value is a valid index, especially since we have never specified how many lists we actually have. So we should probably start by creating a new array, maybe with no entries first. Not like that. What's happening? New list. That. And then later in here, we might have to check if that is null and initialize that index if it's missing. And we might have to actually increase the size of the list. Let's start with just 10. 10 lists in the first place. And for the index, we might have to do something clever. List index could be anything, but we need to limit it to values that are valid indices for our lists array. And there's a simple operation that you've seen before, which can help us with that. It's a modulo. This way we limit the output of list index to a valid index within the total list. if list has 10 possible entries, the values can go from 0 to 9, the valid ones, and that's exactly what this module will generate. No matter what value you feed in here, no matter what positive value you feed in here, because of the modulo, it will be 0, 1, 2, 3, and so on up to including 9. And that's what we store in here, and that's a valid index. And that's how we can operate that. That's a very important concept. And it's what's giving our special set here the name, the title drop, the hash set. Because it's a set that's using hash functions to speed up the process of finding items and manipulating items. So let me remove this code first for now, just get the basics back, because we're gonna have to re-implement everything. Let's just leave the scaffolding for now. Let me drink something first. Okay. So using hashes, we can take a value and predetermine one of many possible lists in which we have to look for the item. If we want to check if it exists, either to just know if it exists or to know if we have to add it a second time, or not a second time, if we have to add it at all, or to find just out where we have to remove it. So any operation inside the hash set would first find out which underlying list we have to use. And then we perform the same operations we did earlier with our first implementation, just inside that small list. And because adding and removing is easier with a linked list, we're going to assume that our hash set will also use a linked list internally. Linked lists, however, do have some drawbacks in terms of performance. That's where the second big topic comes in we have to address. We always had either a linked list in the past or an array, and I introduced them as two different ways you can store large amounts of data without having specific variables for them. We've never discussed a hybrid of the two, and that can go in two ways. We can have a linked list which stores arrays. So we might have 1, 2, 3, an array here, or whatever, and that points to another item which has 0, 2, 3, and that again points to another object that stores maybe just 2 items. The last one is open, free to be used. 9, 8. Okay, that looks more like a 5. Let's do 5. We wanted a way to do it. I have to address, this is not a tree. We're still talking about arrays, simple arrays in a linear linked list. In general, the previous concepts all apply to linear lists. Completely normal lists. We're not talking about trees yet. That's an entirely separate, larger topic. In this case, we just have, instead of a single value in each link in our list, we have multiple values per link, which is a valid structure you can use. And I've actually used something very similar like this already for a very specific use case. To be honest, I don't know if these are good data structures. I see advantages, I see disadvantages, and I'm not knowledgeable enough about the deeper inner workings of C# to know how they compare in terms of performance. I'm using them for one case, and so far they've been working great there, but that might be just pure luck because of that very specific use case, so I don't know if this is a good system. I just know they exist, they're a possibility, and there might be cool things you can do with that. But this is a linked list as a basis which stores internally arrays. What we're more concerned about is the opposite. A linked list which is based inside an actual array. Let me give you a couple of numbers here. Let's say I create a new array. Actually, can I draw this up? Like that. And let's say we start in here. It's 4. And then we go 2. And that goes to 1. That goes to 5. And that goes to 3, and that goes to 0. Imagine this is an array which stores integers. But the special thing about these numbers is that if you look at any index and take the value contained in it as a new index, you get to another point in the array, which itself always contains a value that can point to another part of the array. And oh wait, stop, messed that up, sorry. I was looking at the numbers, I was doing it wrong, like that. So 4 was looking at 2, was looking at the 1 is looking at the 5 is looking at the 3, and the 3 is back to 0. We have a complete circle. We go through all the different values inside our array just by following each value as an index. This is basically a linked list. In this case, our linked list actually is a circle, and that's from last time. We usually expect a linked list to have a start and an end. Worked out quite nicely in this case. We could also just go, instead of a 0, we might set this to -1. So it's not a valid index anymore, and we know the list stopped here. And we can still use it like a linked list, just normally, by doing some interesting stuff like removing this 5. If I want to remove this 5, I can just mark this as invalid, -1 now, and this 1 is going to be changed to a 5, and now points directly to the 3. Still the same procedure as we did here. We just redirect the pointer from one item to 2 items further instead of just 1 item, and that way we remove an item. We can do the same in here. Just before, in the traditional linked list, this value up here is just gone forever. We don't have access to that anymore. That's for the garbage collection to sort out. If we base everything in an array, we have to keep track of that value ourselves because it's still there. It's still in our memory that we reserve for the program that we have control over. We just manage it by marking it as invalid and otherwise ignore it. Unless we want to add a new value. Because let's say I want to add another value in this list, another node. Well, I have 2 free spots now. I have this spot, which is unused so far, and I have this spot, which is unused so far. In that case, I can just reuse one of these 2 spots, put a value in there, and have it linked to another part of the array again. So, while this all is a large array, we do not have the case where the indices have any inherent meaning or relation to one another. The relation of the different indices is entirely determined by the data stored at each index. So we cannot just read through this array from index 0 to 5 and derive any meaning from that order. It's not even the case that every single value in between will make sense, because some values are just completely unused. But if we treat this as like a linked list, it's perfectly valid and we can use all the values we see in that linked list and it just works great. And the reason we do this somewhat more complicated method, keep in mind in this case, we didn't have to do everything ourselves. We can just let the compiler or the runtime do that for us, is that this is a lot more efficient in terms of memory. Because the garbage collection has to take care of this, we increase the workload the runtime has to do for us. And unlike us, in our case here, the runtime might not actually know what to do with this right now. We know exactly what to do with it. We just keep it aside for later to reuse it. Garbage collection has to first check, do you actually need this anymore, or is it really gone? And what do I do with that free memory that's somewhere inside the main memory? It's not neatly stored in one place, in one location where everything is already nicely compacted. No, it's somewhere. We have to reuse that memory for something else maybe. And if we need new items, we probably don't reuse that one because the garbage collection is still busy with cleaning that up, and we have to reserve more space somewhere else, which also has to be found first. All that overhead is gone because we have to do that ourselves. And because we already know exactly what we want to do, we can optimize our code to do that more efficiently than the garbage collection can for this more general case where it doesn't have the info that this is all part of a linked list and you can optimize for that. So instead of leaving it to a system that does the job, but not very optimally, we can do a very specific program ourselves, which is more work, but will be more efficient. Plus, the entire overhead for the memory itself is maybe a bit less because we don't have individual objects somewhere in the heap that take up memory. We only have single values or maybe pairs of values because we actually don't want just the index, we also want some value to go with it. That's still technically a bit less overhead, a lot less work for the garbage collection, the entire memory management, and we can write algorithms specifically optimized to deal with the situation, to make the entire process easier. So overall, more efficient code. But it takes a while to wrap your head around. And it gets especially nasty once you have to combine it with the HashSet. So maybe let's ease into this. Let's start by just creating a single list for now. A single linked list implemented inside an array. All right? So we need an array of some type that can store our data. It's called items. What type do we use for this array? I used int for my demonstration, but that would just be a single value which is used as the pointer to the next item. Usually if you have a linked list, you probably have a class like this, link, something like that, and you have maybe a value and big link next. That would point to the next item. Because we're inside an array, we don't use the data type itself. We can use an integer because we only need the index. We don't need a full pointer inside memory. We don't need to store an address to our heap. We can just use an integer, and we know that refers to our specific internal array, and we know the logic for that. Simple data type, easy to understand. We still want to store a value, which in this case is of type T, it's the generic. And we can just store that in here, inside an array. But we can be a bit more efficient in this case. We don't want to store an array of addresses into our heap, because if we just do this, then our linked list will still end up like this, because the individual link instances we create will be just somewhere in heap. And our main array will be just a collection of pointers that points to these different objects in the heap. And actually this one, maybe up there, that wouldn't gain us anything. So using a class is not the way to go. If we change this to a struct, however, that changes things, because now the entire memory that we use will actually be completely contained in this one array. Actually, we have a large array. Actually, let's large array like that maybe, and we have value and next, value next, value next, and these are our structs, but they're fully contained in memory, just one after another, with absolutely minimal overhead, and all in one single chunk in the heap. So the computer only has to reserve memory once, and once that's done, the memory management has no more work. Like, we don't have to add any pressure to the garbage collection with cleaning or reserving anything new until we run out of space and we have to get more data. We'll get to that. But by using an array that internally just stores structs, we can make very efficient use of the memory and still have all the features of the linked list. So that's the first one. Now that we have our items, we should also initialize them. For now, let's just initialize them with 0 entries. Doesn't really matter, we increase the size anyway. Just for now, except we should start with empty, because we might not need any memory if the set is never really used. And in that case, we don't want to reserve any space we don't need, maybe. Yeah, I said we did the... Yeah, let's just use the normal... We're basically recreating our very first prototype of a very simple set without the hash part yet. So just the set with the basic functionality that has to iterate through all the items, just to get the same thing but with an internal linked list. Yeah, let's start there. To add an item, actually, no, let's start with contains. That might be the simplest one. How to iterate through everything. First, we should check how many items are actually in our array. Private and count. Because we might initialize it with 10, or maybe later it will have a large amount of space, unused space. Keep in mind that once we use our array, we can at any point remove data, and that leaves little empty spots. So even though the array has a total of 6 possible items, only 4 of those are used. These 2 are empty, and they're not in the end position here. So we need a separate way to store the information how many items are we actually using right now. Of these 6 possible spots, how many are taken? And how many more spots can we take for additional items? And that's what the count is for. So we can, in the contains, first check if count less than 1, return false. Because if there are no items in our set, well, the item cannot be in there and we can just return immediately. Simple. Also resolves some edge cases, so should always include that. Now we have to check all the items in our linked list. Well, we need some way to start off. And earlier I did so by just starting at index 0, but you might delete the value at index 0 at some point, so that's not a good start. We need another variable to track where our linked list starts. First item index, let's put it like that. So this is our entry point. This would be the start, the first item, the head of our linked list. Just an integer, which is the index in our array where the very first item of our linked list is stored. And from there, we just have to iterate through all the next values in every single item to get the next item. Item, item, item. And that's how we iterate through everything. And that's what we can use a for loop for. Keep in mind, for traditionally would just increment or decrement a single integer variable, for example, int I equals 0, I less than something, something, something. That's the classic one. But it's just a loop with 3 different parts written in a single line. Convenience. We can do every type of loop with a for loop. We're not constrained to just incrementing or decrementing an index, for example. So you can use an int I. We set it to first item index, for example. And as long as that I is greater or equal to 0, as long as it's a valid index, so as long as it's not -1, we want to continue. And in each loop, we want to advance I to the next component, the next value of the item at that position. Right, keep in mind, we are now using the index inside the items array to target a specific link. Actually, let's rename this now. Makes more sense like that. Right, so this construct here is the same as if we just had before, like term first dot next. So if this was the normal linked list with classes, we would write something like this. We had a first item, which is a type of item, and then next would be another item that we can iterate into, and then we had next.next, and so on. That's what we do before. Now everything is organized through the integer, which gives us an index in the items array. So we don't address items directly, we do that indirectly through the index in the array. So this is always the same as just referencing a specific item before. Don't try to think too much about it, maybe, or think deeply about it. Either that. Don't do it half-assed. Either just accept that this is the same as writing a variable for a very specific index, like getting a very specific address, or you think deeply about it and think about that this is the index that we use to access a specific value inside the array items. That needs to get into your head, because we will use this a lot, and it might get confusing if you don't understand that part. So this will start at the very first item, and we know there is a very first item because we already exclude the possibility that there are no items, though this will be a valid index. We do check it nonetheless, so in theory we could leave this out, but we leave it in for now because consistency. And once the loop iterated once, we will advance I to the next index that we get from that item. And inside the loop, we make a comparison. We take the value, can just use this again, of that item. Oh, wait, sorry. I made a mistake. That was, of course, only valid for the very first iteration. My bad. This is setting to I, this is I, yeah. Okay, this is the construct that refers to a very specific item. Ooh, I think I'm getting out of it, and we are only halfway done. Okay, yeah, today's gonna be longer. Have to take a small break in a moment. So each position, we're now gonna take the item, and we take the value from that, and we want to compare that to the input item. That's equals, same as before, item. If it's the same, we return true. So we can remove the brackets now. Essentially the same logic as the manual approach first with the for each loop in the beginning. Just go through each item in our linked list this time, array-backed linked list, and we compare the values, and if it's the same, we can abort and return. Done. And if we didn't find it, we return false. Now, depending on how I implement things, you could, of course, also decide to just go classic I equals 0, elas length, lie. So just iterate through the entire array. And you now would have to somehow verify if this item is real or not. Because every position in the array will have a value for value and for next. But okay, cool. Auto mode works. Just had to ban someone. Good to know that the basics in Twitch still operate as expected. Okay, yeah. In our array, every value will be filled with a default value, which means all bits are 0, which means this value will either be just a 0 or a false or a null, depending on the data type, depending on what data type T is going to be in the end. And next is always going to be 0, at least so far. So we would have to somehow distinguish a valid position, one that's actually used with real values, from one that's using just the default values. And the only way we can do that successfully would be if we had some additional flag, some who used maybe, check that, but that's wasted memory. But then you could just check if the item position is used, and if not, you ignore it, and if it is used, then you make a comparison and go to the next. So it is possible to just iterate through the array directly and ignore the order in which items are laid out, but it's easier to just go through the linked list as intended. Don't get distracted by it being an array. For these operations, we treat it like a linked list and ignore that it's an array. You have to blend that out. That's the contains method. Let's try the add method now. Add is a bit more complex, because if items doesn't have any more spaces free, we need to increase the size of our array. So first, let's make a simple check. This time not if count is less than 1, but if count is greater or equal to, no, that's fine, items length. And if that is the case, we have to increase the size of the array. And if not, we can just continue. But the code we write down here has to work in any case. So we have to prepare the array so that once we get down here, items will have at least one more space free for the next item. And increasing the item size, we've learned that in the list episode. Just determining a new size first, and new size, and we can do that with items.length times 2. For now, let's just do it like that. But we have to include the option that length is 0, like it is right now, if it's the first time we add something. So we'll make a simple ternary expression here. If the length is greater than 0, we just multiply it by 2, double it up, and if it's 0, we just add 1. For now, let's keep it simple. Not ideal, and we will have to revise this later, just so heads up. This method of increasing the size of the array is not a good way to do it for hash-based systems, for hash sets, for example. So doubling up the size is great for a dynamic array, for a list, but it's problematic if we're talking about hashes. But we'll get to that later. It's one of those math things that I do not fully grasp myself, so I can only give you some hints of what this is potentially about. Yep, and basically this, we create a new array, and then we just iterate through all the positions, 0 less than items.length plus I, and we copy over the data from new items, no, 2 new items from items I. Yeah, that works like that. We only go through the length of the old array. The new positions that we've added will be just kept as their defaults. Defaults? Defaults. Defaults, defaults. Is that a word? Defaults? Defaults? I want to default something, I want to invert it? Could I say a default something if I invert it? I'm inverting a default value. I defaults it. In case of... Never mind. Those are drunk conversations, not something for a lecture. And once that's done, we can just swap the addresses out, and items is now a new array with at least one more space. If it's 0, and we can remove this to the default expression now. And otherwise we double it up for now. Okay. And actually, instead of doing this, we could do a different expression. So this resizing of arrays is a very basic method that has to be done in a couple of cases. So we already have something given to us by the default language libraries. We can use the class array, which handles arrays, surprisingly, and it has a couple of very cool functions that we can use. And one of them is resize, which uses the ref, which we've talked about. Could do it like this, and internally it will create a new array, copy the data over, and then assign the address of that new arrays to the variable items that we have in here. Keep in mind, this is a ref. This is not changing the actual array items. It will create a new array and just replace the meaning of this variable. It will give it a new address. But the original item, or the original items array, still exists in memory. We just don't have the address to it anymore. So this could work. So all we did here could be replaced by this call. I left it as this manually because we're gonna do something with that later, where we want to go through each item manually. But for now, that works. Array also has some other cool features we could use, by the way, but yeah, again, later. We don't use them. So at this point, we know the array has enough space to add a new item if necessary. Now we have to also check if that is necessary at all. And I guess in this case, it's probably better if we first check that in here. We can just use our own contain method, and if contains, turn false. Now logically, I would actually prefer to do it down here, just because I find the logic to be simpler that way, but it's not as optimal, because this way we first check if we need to add something, and only then will we bother increasing the size. If I check afterwards, we might increase the total size of our array, only to realize the item already exists and we don't need to add anything, and that's just waste. But yeah, the order could be anyway. Let's do the optimal one now, and maybe switch it later if necessary. But we checked the item doesn't exist, and we've increased the size of the array if necessary. Now we need to add the item. Where do we add it? Let's go back to the drawing board. Why is screenshot not long left? What happens? All the time. Okay, let's try this again. Is it timeout maybe? Okay, then we can see it again at least. In this example here, we have some spots that are free to be used, but we don't have an obvious way to detect them. At least right now we're not marking them in any way, and we want to keep it that way actually. There's a simple way we can track these. And actually let me make a larger one. So let's make some entries in here. We have the value and we have the next. Like so. And value could be anything, we don't care about that. And next, well, we might have our first, which points to this one, for example. So first item index, our variable internally, will point to index 1. So this one. And this might point to 2. I mean, just because they can be all over the place doesn't mean they have to be. They could actually be ordered and sorted nicely, the same order they would be if we just added them in the array one by one. It's just not likely to be the case after we have many operations happen on there. So we did a couple of deletions first, removals, and then additions, but it can happen. At least in the beginning, it's quite likely. Now this one might point to nothing, it's -1. Still a valid value, but just doesn't have a next item in the list. So this list only has 2 items. So this one and this one is free. These 2 items are ready to be used for our use case. How do we find them? If we mark them, we have to waste memory in some way, either directly in here or in some external structure to keep track of which indices are usable and which are not. And that will change a lot depending on how many we add and remove in between. Whenever we add a new item, well, we lose one we could use. So there's going to be a lot of change in there. Sounds like we could use another linked list to keep track of that. What if we had a linked list specifically to track which indices in this array are free and which are not? Every time we add a new value to our array, we remove that index from our specific special linked list. And whenever we delete an item, and so we have a new index free in here, we add it to that special linked list. Linked list allows to freely add and remove stuff without much consequences. And we already learned this trick here with the array that includes a linked list internally, which saves the resources. So let's use that again for the secondary linked list again. So we have another linked list inside an array, which also has some free spots that can be used and some used spots that indicate free indices in this first array. So we need another internal linked list that keeps track of which indices are free in this linked list, so we can figure out which are free in this one. So that's probably not the best way to do it. We can, however, and that's one of the clever things in that specific implementation that I just love, reuse this array to hold the second linked list as well, the linked list for free items. There's no reason why these spots in our array can only be used for one single linked list. Since these positions aren't currently used, we point only to this index and that points only to that one. The first and the last are free to be used for whatever else we need. Like our linked list, our main list doesn't need them. So we can just have this one, for example, point to 3. And this one then maybe to nothing. And we can store a pointer to the first element of the second list. Just store the index to that first item of the free list. And inside the free list, all the unused positions are tracked. This way, every item in our array is always used. It's either used for the actual main list itself, or it is part of the other list with unused indices. Does that make sense to you? Not all items, not all positions inside our array have to be used for our main list. So we reuse them for another list. And because they're not used by the main list, there's no conflict here. We do not steal any valuable space because it's not needed anyway. We just use the features we already have, the existing data structures, to organize the unused parts to make it easier to see where I can find something to use. So when I need a new item to put something into, I just check what is the index of the first item in our free list, which is 0. So I would just change this one here. This one now points to... Okay, this is a larger process, so let's maybe reset this first. So the addition, as we're going to implement it now, would have to add an item to this existing structure. We know there's enough space. We have only 2 items stored based on count, but we have 4 spaces in the array. So there is enough space. We now have to first figure out which item can be used to add the new value. And our list of free items tells us, oh, index 0 is unused. So we use this value now. We fill our item in here. And when we've done that, it's no longer a free item. This is now used. So we change the index for the first free item from 0, the one we're currently working on, to the item we are currently pointing to, 3. And instantly we still restored the old order. We still have a fully functional list which tells us exactly where to find the next free item when we need it. But the first item is now ready to be filled, ready to be used. And in fact, we have already added our value. And what we do now is also change the first item. Just change this to 0 to point to the first item here. And we change the item we point to what the first pointed to earlier. Like so. It's a bit longer in terms of the logic here. We have to write this out now, but the basic process will always check if we have enough space, and if we have enough space, we just grab an item from the secondary list, the list of free spaces, free indices in our array, and we use that index by removing it from that free list and adding it to the main list. And later on, when we remove an item from the first list of the main list, we're adding it back to the free list. So we're only switching the assignment of an item in the array between one of these 2 lists, always. Now let me just, before continuing, let me just quickly take a short break. I'll be right back. Okay, sorry for that. My nose was killing me. So, we always one of these two lists, which work the same way, they just have different purposes. So instead of first item index, we also need the second one, first free item index. And actually when we start out our entire tool here, first item index will be -1, because we don't have a valid one yet. First free item index will also be -1 for now, because we also haven't initialized anyone there yet. Things will get interesting in a moment. Just give me a second here. We have to figure out which index can be used. So we find out index to use. That's the value we want to fill. And let's assume we do some stuff here to figure that out. And once we know which index to use, we can then index to use, set the value in there, item. It complains right now because I haven't assigned a value to that yet, so just ignore it. Items, index to use. Next, it will point to first item index. First item index will instead now point to index to use. And we increase the count of items because we have one more. And then we can return true because we've added an item. So we stop here. Let's just assume right now index to use will be always the first free index. So index to use equals first free item index. So this is the index we're going to use now. So we have to reuse that for our current application, or for our current algorithm. That's the part we've done already. And we have to clean up the old list by removing it from there. So index to use is the first free item index. And then first free item index will be set to whatever next we have the next to use. Next. So we take the item, the first item of the free list, and reuse that to fill in our data and put that in as the first item of our main list. The thing is, when we initialize our array, there are gonna be a lot of values in here with only default values, which all point to 0 and not to each other. And that's not ideal, because now they are neither part of the main list nor of the free list. We could, in theory, initialize the array and make sure that every position points just to the next item in the array. So when we resize the array, initialize it basically, we can make sure that all the items that are not already initialized before, that we copied over, will be added to the free list. But that's extra work. Completely unnecessary extra work. In this constellation right now, once we exhausted the free list, once we also added the second item, so this one is -1 right now, we occupy next item. This is pointing to 0 now. Like so. Once we used up all the 4 spots in the beginning here, the free index will be invalid. It's -1 because it's not a valid index. There is nothing usable in here. Oh, actually, that's something we have to change still. Okay. Admittedly, that's something we have to change. But the basic idea is that once we filled out these 4 spots, only then do we actually need to look at the items that come on the right. As long as there are still 3 items in here, that means we've removed items that have been previously used in this block here. As soon as we remove an item, it will be removed in one of these spots we've used. Can be the last one, can be the first one, anyone in between. We reuse all those items, and only once all the possible spots are filled, do we actually need to go to the next item in the array to include a 5th one. And when that happens, when we do not have any more free items, if we've used up all the spots in our array up to the full count, so if it's one continuous block of valid used items, then we know the next item in the array will be usable and free. It has to be. Maybe try to think about that a bit more, why that is true, because I'm not bothering explaining this right now. We've already spent too much time on this. So if free first item index is greater or equal to 0, if we do have a valid first entry, then we're going to use the free list. Else, well, index to use is just the next item in our list. So if we use already 4 spots in here, our count will be 4. So index 4 is the next one we can use, and that's free. And once we've used up this value, it will be part of the main list until we remove it, at which point it will become a part of the free list. So the moment we use any value, any index in our array, it will forcefully be added to one of the 2 lists. And once it's in one of these 2 lists, it will remain in one of these 2. We just switch them back and forth between them. And if the free list is empty, we know we can just go to the next index in our array, and it will be a free item. So this is that part. Well, the only thing we have to change up here is to make sure that all the other items, the free items we might grab, actually we don't have to do that in here. Yeah, never mind, we don't have to do that yet. Actually, that's a different story altogether. No, that's it already. We either grab the first free item, or we grab the next item, unused item in our array, based on the count. And because of the way we use the logic, because we only switch between the 2 lists as long as they still have space, the total count will always give us a free item. This only works, of course, if the count is equal to the number of used spaces in our array. That is only true if the free list is empty. So, yeah, maybe that makes total sense to you and that's obvious. Maybe you have to look at a diagram and experiment with removing and adding values to an array and see why that works. I was a bit confused the very first time I saw it, because I wasn't thinking about that optimization. I was thinking that, yeah, of course I have to add everything to a list in the first place, initialize it with that, and then reuse all the items. I didn't think about just keeping everything in the start of the array and only expanding when needed, which it's obvious now, but it's one of the cool things in there. I've learned so much by reading that code. And it's only the start. There are so many cool optimizations we'll get to later. Yeah, so that's the add method and the contains method. Not the remove one. We can make, again, check if there are any items at all. Because if there are no items, then we don't have to remove everything. And now we have to first step through the array again, or the linked list specifically, and check if we can find our value. If we cannot find it, we can just stop. So, turn false. If we didn't find it in here, well, nothing to do, return false. If we do find it, we can return true, but now we have to delete it. And to delete the item, there are one of two scenarios. Option 1, the item we want to remove is the very first item in our linked list. So our index, our main index that starts the list, points directly to it. And the way we handle it is we of course add it to the free list, the same way we add items to the main list. But to remove it from the main list, we then either have to change first the first free index, or we have to change the next of one of the items in between. So if that's the first one, we remove it by changing this value. But if we remove this one, for example, the first index, we have to change this address here to 1, to skip one ahead, one item. So this part up here. We remove an item by just advancing the next of an item, and then it's forgotten. So first we have to check, is it the very first item? And potentially we have to know the previous item. So, last equal -1 equals I. So I'm adding a second variable here to I to keep track of the value I had before. Because if we remove the item in between here somewhere, like in this case, we have to know where we have checked the n. So if we find this value is equal to our item, we have to change the next value of the item we came from. So we have to keep track of where we were before. That's why I have the last, which always just stores the previous value of I, except for the very first iteration where it's just -1. But after that, it's always the last I, and then I is advanced to the next item. So if last is less than 0, so if it's the very first iteration, if it's the very first item, we can send first item index to items I dot next, because the first item can be skipped directly, and items I dot next itself will point to first free item index because we added in there. And for first free item index will be set to I, because that's now the very first item in the free list. Pretty straightforward. That is if it was the very first item. If not, then we can leave out the first item index as it is, We have to now change items last dot value not value, sorry, dot next to the item that we currently point to in our current item. Skip ahead. And then we can copy that over, because that's basically the same logic. We add it to the free list. And because it's the same logic, we can actually move that out here. And just do it like that. Take a moment to look this over, see if that makes sense to you. We're either the first item in the list, in which case we have to remove or change the value of our head of the very first item index, our starting point, or we somewhere in between, so we have to bridge the previous item to the next one. And in both cases, the item we've actually removed becomes now the first item in the list of free items. And if the list of free items was previously empty, this will be -1, and next will be just pointing to an invalid value and can be reused all the time. So that's not an issue. Technically, all we have to do now is remove the count, or decrement the count by 1, because we removed an item, and that would work. There's one thing we should do, however. One more thing. And items I dot value equals default. Why do I do this? This has to do again with memory management, and for something like a string that can have influences. For if it was just integers, this doesn't matter at all. But if it's a large complex object, this might be extremely important, because this determines whether or not we still keep an active reference to an object in the heap. If we do not do this, our own data structure might inadvertently keep an active reference to an object that should be discarded, that's not used anymore. And it's doing so inside memory space that we consider discarded ourselves. Keep in mind that we took the entire memory management for our internal linked list away from the runtime. We're doing everything ourselves now, so the runtime is not removing anything from this array. It's leaving it for us to do. So if we do not free it manually ourselves, the original value will stay intact until it's overwritten at some point. If it is overwritten at any point, it might never be changed at all. And that can have dire consequences. It can. Doesn't have to, it's probably won't, but it can. So this is actually pretty important. And with that, we have the remove method as well. And we can test our code. Sorry, we can test our code again. Unless I made a mistake, I hope I didn't. Let's just try it. So, what was the logic? We start with just an add that should get us a true. Correct? This should get true as well, and this one as well. This should get us a false. Correct? This should also get us a false. This one should be true. Great. Removing this should be true the first time. This doesn't exist, should be false. We already removed it, so it should be false as well. So far everything worked, and now we should only get the B. B exists more than once. Perfect. So our changed hash set, or well, in this case just set, works. So that's great. We have a working set using a linked list embedded into an array. Slightly more complex, but perfectly viable. Now comes the interesting part. We have to combine it with the idea of having multiple lists. Now, you have already seen that there is no real issue in having different linked lists in the same array. We already have two different lists right now. One our main list, where we store all the items, and this one, and one storing the free items that we can reuse, like our recycle bin, for actual recycling. The same logic can be applied to many more different lists, which all are contained within this one array. We still only have one list that contains free items to be reused, because we don't care what an item was used before for, which list it originally came from. It's just free spot to be used. However, we might have multiple different lists that we have to manage. And having different variables for each of them, that's not appropriate. It's more work for us, and it would limit us to a very narrow band of possible hash values. So instead of a single index, we store an entire second array just for indices for... where is it? Okay. First indices, something like that. Each position in this array will be the same as our first item index before. Just each one represents a different list. And these are also called buckets. Each bucket contains a different list. And technically this could be the free bucket, the free item bucket. I'm just gonna leave the old name so it makes more sense. But this is the term we will probably use. And we're gonna have to initialize that, of course. We're gonna start with no entries, because why should we have any buckets if there are no items to store anyway? But now things get a bit more interesting. Let's start with the contains again, because it's the simplest one. To check if an item is in our list, we have to first now figure out which list to check in the first place. This assumed that there's only one linked list in our array, one actual usable linked list. Now, however, we first have to figure out which bucket we are referring to. Which bucket are we taking the list from? Each bucket represents a different list. And that means we have to do the hash first. That leaves us the question of what hash function do we use? In my example earlier, I first just picked some random ones and then finally arrived on some sum value. But how to create a hash value depends on a lot of factors. Depending on what data you have, it can be a very complex task or it can be very easy. And we also have to determine what kind of value we generate. Because no matter what data we have, we always want to have the same type of data that comes back. Our hash function earlier, the getHash, the pseudo function I wrote down without content, returned an integer. And that's a good value to use. Integers are nice to work with, easy to work with. Let's just keep that in. But to generate the hash, we would need some way to analyze any kind of data, no matter what it is, and generate a reliable hash value. That's no easy task. It's actually an impossible task. The reliable part, at least. But only for us. See, the people writing the different types of data we want to store, they might understand their own data structures, their classes and structs, and they might have a good idea of how to generate a good hash based on that data. And so they probably wrote a method in there to generate a hash, a more reliable hash than what we could come up with. If they didn't, we could rely on the runtime to provide a value. Maybe not a good one, but at least a value. And if they didn't implement it, great, that makes just everything a bit more efficient. And because hashes are very useful for a lot of things, it's one of these very fundamental methods that are baked into every single object in C#, whether you actively write it or not. Just like toString is a method that exists for every single object that always allows you to generate a string from any piece of data, you can always generate a hash code from any piece of data. So I can item.getHashCode. That is a guaranteed method. It exists automatically. There is no way it doesn't exist. Doesn't matter what type T is. And it might be a default implementation by the runtime, or it might be an overwritten version of the method provided by whoever created the class that T is used for. And that leaves us with a hash code, an integer value, which could be any integer value. And just as we did earlier, we want to then use a modulo based on the list of buckets. And that gives us an index in our bucket array. And that index in our bucket array will contain a value that is a second index for the actual main array that refers to one of the potentially thousands of lists in there. Things get a bit weird now. We have indices that point to positions that contain another index that point to positions that initiate a sequence of linked indices. It's a bit tricky to wrap your head around the first time. At least when you write the code the very first time, you will stumble across this a lot. Like, am I the first index or is this the second level index? Which index am I in? So it's important to keep the naming conventions somewhat consistent throughout your own code. But yeah, this is the first level index, the bucket index. This determines which internal list we're looking at, which one of the many linked lists we're interested in. And we have a slight problem here with hash code because it could be any int value. Int can also be negative. And while you can use modulo just fine with negative values, that means the result would be negative, and that wouldn't be a valid index anymore. So there are two ways we can handle that. We could just make a simple ternary here. Hashcode less than 0, then minus hashcode, otherwise hashcode. So if hashcode is less than 0, we invert it and just use that. That immediately halves the potential values we can use, because that means even if two different items would generate two different hash codes, one might generate 5 and the other -5, we would treat them as both using 5. So that's not ideal, but we are forcing all the hash codes into a very limited amount of potential buckets anyway. Like, an int has 2 to the power of 32 different values. That would be quite a lot. If each bucket is just 1 bit, that would still take us 2 gigabytes to store. That's not going to happen. So we're not going to use all the values the hashcode can provide anyway. So just halving it here, just slashing it in half, the terms of possible values, that's fine. What's a bit more annoying is this ternary. It's a bit ugly to look at, and comparisons are fine, but this branching is not always the fastest. So we can make our life a bit easier by doing a bit of bit logic. We can use an AND, and thank you. We can take our original int value, which is just a 32-bit number, where we use the very first highest order bit to determine if it's positive or negative. That's the 2's complement, we've talked about that before. If the very first bit is 1, we know it's a negative value. If it's 0, it's a positive one. And we can simply make a bitwise operation here to force a value that is definitely positive. We just have to create an AND, bitwise AND, with a value that has ones in every position except the very first one. So let's do it the interesting way first. We start with a 1, bit shift that over by 31 positions. So this right now would be a 1 followed by 31 zeros. We want exactly the opposite of that, so we invert it bitwise. And now we have a 0 followed by 31 ones. Because I have an IDE, I can just do this and already generate the exact value it would be. This is the highest positive value you can store inside an integer. If you increase it by 1 more, you have the overflow and get to the smallest possible value, a negative one. And because remembering this value or writing this out is a bit annoying, you can also just use int.maxValue. Because again, integer is a data type, but it's also a class, sort of. And we have some useful properties we can use. In this case, a constant which stores the highest possible value. So this is one way to do it. Convenient way to convert the hash code into a positive one, force it to be positive. We squeeze it into the limited size of the bucket, get an index. And so instead of first time index, we get to the buckets, and from there we get buckets index. The position at buckets index. So that's the change. Instead of just going to the list directly, we first have to generate the hash code. And based on that, figure out a position inside a secondary array of possible indices, each index referring to its own unique lists of items in the main array. So we would have something like items, buckets, list index, whatever. So we would have the value of the first array gives us the index for the second, for which we can then get the value. This is where the head scratching comes in a bit. You have to keep your indices straight. Buckets contains just the indices. Items contains the actual values plus indices in the form of next. And we have an index in buckets, which gives us an index in items, which gives us a value. First level index, second level index, value. That's something you have to contend with. It might take a bit of experimenting again. At least the very first implementations I tried, after learning how everything worked and trying to retrace the steps, I slipped up a lot. A lot of errors with that in the beginning. Let's try the same now for the remove method. We generate the hash code. We remove the sign bit, force it to be positive, get the bucket index just like before. And then in here we go for buckets, bucket index, just like with the for down here. And we have to replace this as well. Index, like that. And that's already all the change we need to do in here. Things get a bit more complex in our add method. Sorry, just have to interrupt, right? No, I'll be right back. Sorry, I had to deal with an open window right quick. Getting dark and we don't want it to rain in here. Not that it's raining right now. Or maybe it is? Maybe it's a snowstorm. Or a hail storm. Maybe a sandstorm. Whoa. Where was I? Right. So it's getting a bit more complex in here. Let's first go down here where we still have to figure out which item to use in the first place to place our data in. So we have to get a free index in our main array. That's still using just the one singular shared free index linked list. Everything is fine. But then here, the first item index, same logic as before. Grab the hash code, make it positive, fit it into our buckets, and then we go to bucket index, like so, and fill it in. So that part, the same change we did down here. Easy. The part that gets tricky is this up here. Increasing the size. Because now we don't only increase the size for our items, we also increase the size of our buckets. Now the way we grow the buckets doesn't need to be the same as the growth rate for items. But it might be the best version you can work with. You can have situations where you think maybe my bucket should be smaller or bigger than the amount of items. Well, at a very specific time at least. Ultimately, it doesn't make sense to have more buckets than items, unless you know there are many, many more items coming. Having a smaller bucket size could make sense if you think that you won't find a good distribution of items, but usually, ideally, if everything works perfectly, you will fill out your buckets, where each bucket refers to exactly one item in your list in the main array, and each sublist will just be one item size large. So that would require to have as many buckets as items, and that's why we grow buckets to the same size. So buckets, not buckets like that, and new buckets size like that. And we copy all the old data over. That's also fine. But we have a slight issue now. Let's get back to the drawing board for this one. Yeah, it has to be timeout. Screen share is gone again. Have to see if we can turn that off somehow for the next stream. Is that a new page? So we have, I'm not gonna bother making this pretty right now. We have our buckets, which point to different parts in the original array, which itself might point to different parts in the old array, in the main array. So this is our actual items. buckets. And the position inside our buckets array for a specific item depends entirely on the hash and the length of our buckets. So if an item inside our list here, let's say this is a 1, right? And if we hash our 1, it would give us, would it give us a 5? Okay, let's say our item 1 would generate a hash code of 5, and we have 5 positions in our buckets array, modulo 5 for the total length is 0, and that's why it's in index 0. In here, index 0. So item 1, item value 1 generates a hash of 5, modulo bucket length 5 generates index in the bucket of 0. And so position 0, index 0 in buckets, points to the items array where we store the value 1. That's the logic right now. If we increase the bucket size to 6, this would now be modulo 6. Well, actually, no, that's fine. Modulo 6. That changes the outcome. It's not 0 anymore. It's 5. So now when we try to figure out which bucket to... What the hell? Which bucket to look for item 1, we go to index 5. Index 5 doesn't point to anything right now. It certainly doesn't point to the position items where we store 1. The hash code remains constant, that we don't have to worry about. Well, technically it can change if the person implementing the hash code method didn't implement it properly. But generally the hash code will be always static, will be the same at least. Can rely on that, but our bucket size will change over time. And that means the position for each list has to be stored in a different position in our buckets. We have to completely redo the content of buckets. We can't just copy over the old data. So when we create a new bucket array, we can't simply copy over the old data. We have to recreate it entirely. To do that, we can use our old code again. Let's just use shorter versions of that. Hash like that. Create the hash. We store. We get the hash. We figure out which bucket to put it in, but we do that based on the new bucket length, which is new size, so we don't have to look up length ourselves. Like that. And index is now the new index in bucket that we would store the item at position I. And we have to put in bucket position index value of I. Take a moment to look over this. We still copy over the data in our items just like before, 1 to 1. We don't change anything there. The new bucket has to be filled entirely new. We cannot rely on the old indices anymore. All the old bucket indices are invalid now. They might accidentally be the same, but they will probably change. And so we have to recalculate which bucket we put which list into. And we do that in reverse. We go through all the lists, try to figure out where does the value belong to. We get the hash code for every single position in our old array. And by the way, just a hint of logic, because we only increase the size if we reach the limit of our array, we know that every single item in our old array will be a valid filled piece of data. So we don't have to worry about generating the hash and filling the bucket for an invalid item, unused item. Every item in this if bracket in the old items array will be a valid used data item for one of the lists. Not a free list, not a completely unused item, it will be a valid used item. So this will only execute for actual items, so we don't have to worry about that. We get the hash code, try to figure out where in the bucket this list would be searched for if someone were to pass on the same value into the contains method, for example. And then we put in the value into that expected bucket. But now comes the problem of collisions. That in of itself should make sense, but this only works as long as we do not have any arrays that repeat, not any hash codes that repeat or any collisions because of this shrinking here. So instead of just setting the current buckets to I directly, we should actually fill the entire list, the original list, correctly. It's like we're filling in the items the very first time. So our actual item, I, the new item, the new I array, will point to whatever the bucket net index wanted to first. And then we override it with our position. So we insert that item as the first item in that specific bucket list. And now we also handled collisions. Not much different from this code down here. We compare it. We have index for the bucket index and index to use for I. It's the same logic. This part and this part down here. You can also see get hash code is marked here because we cannot be certain that the item will not be null. Nullability is something we have to work around. So instead of doing all of this, we could write a single method internally that will generate the hash code for us. Let's do that. Let's put that up here. Private static int get hash t item like that, and return. Make another ternary item is null, then return just 0, and otherwise, yeah, item hash code like that. So instead of .get hash code, we do get hash dot value like that. Actually, that was the issue we had before, but yeah, I need to replace it anyway. That was not why it complained before. I was just dumb. Get hash item. We still have to work around the nullability of that, because keep in mind we explicitly added a null in here, so if that was null, would have an issue. So the new get hash method works around that. And actually we can do this part in here as well. If it's 0, we don't need to do it, of course, but if it's the normal get hash code, we make that. So we can remove this as well. Hash code. Hash code. Did I forget anything? That. Okay. Get hash, hash code, hash code, hash code. Alright. Oh, also, this should be new buckets, of course. Almost made another mistake here. And then we can set buckets to new buckets. Okay, that way. Took a bit longer than expected. I'm really unsure about the pacing in this episode. I feel like I could make this a lot more speedy, but at the same time I'm not sure if I may be too fast for some of these. Plus 2.5 hours by now. I'm not used to long streams. Okay, maybe time to wrap this up. So this should work correctly already. So if we give that another try. Let's just do it in the speed way. We expect true, true, true in the first 3. Let's do that. And I forgot something. Alright, it didn't continue, so we have an endless loop somewhere. What did I forget? Forgot something. Forgot something important. Right. The buckets. E equals stop length. Then new size plus I. New buckets I. This one. Okay, forgot this one. There's an optimization we haven't done, so I still need to do this. Our new buckets. This also needs to be new buckets. Actually, let's do that internally, completely separately for int I equals 0, less than, let's just do classically. Okay, so the problem is new buckets might be 0, or will be 0 in most cases, and it should be a negative value, -1, to make it invalid. Otherwise, it will just constantly point to 0, and that's just wrong. So this is better. All 3 are true, as it should. This one is false, this one is false, this one is true. That's also correct. True, false, false, correct. And now we should get B is double. Yep, that works. Let's remove these. Guess we can make everything in speed mode next time. That. Actually, let's do debug, right line that way. To have the output in here instead of the console makes things also quicker. Okay, so the basic logic with the hashes works now. We have one main array to store the data in. We have multiple buckets. Each one refers to a different index inside our main array, representing a different linked list. And we have one main recycle list, the free list, where we can grab new free spots in our array for adding new items instantly. We use hash codes to store everything. And that's where we add the next optimization, one of two we're doing before we're ending the stream. Generating the hash code itself is not trivial, not always. So removing the amount of hash codes we have to generate is quite an optimization for us already. Especially when we can combine that with another optimization we can do later. Right now, I have to generate the hash code every time for each item here. And I might have to generate it again every time I have to resize the array. I can just go in here, public, and hash. Store that in our item. I waste additional space in our array, of course. That takes extra memory space. But in return, where do we, there. Can go to items, index to use, dot hash. Along with the value we store, we can just store the hash code. Like that. Yeah, that works. And then up here, we don't have to regenerate it from the item's value. The hash is just the existing hash in our item. So we still have to generate it once, at least for the item we store. But then the hash code is remembered and we don't have to generate it a second time. We still have to generate it anytime we try to get the hash for the item for each operation, but that happens only once. So that's still fine. And this hash in here allows us to do another thing. This equals happens twice. Well, actually 3 times if we include the hidden equals in the contains up here. Equals compares to items, and that is also a potentially long-running process. Potentially. It will probably be very easy and straightforward in most cases, but it can take extra time. We can take advantage of the existing hash value in here, which is an integer. Integers are one of those data types where generating the hash is pretty simple and where comparison is trivial. And we know if the item is the same as the one in our list here, if this comparison is true, then these two would generate the same hash. If they generate a different hash, they cannot be the same item. The hash item or a value generates is always the same, no matter what. If it's the same value, it will generate the same hash every single time. So by first comparing items I dot hash, if that's equal to hash code and equals directly, then it's true. So very simple addition here. We first compare the hashes. The hash we could generate it for the incoming item and the hash we have stored for the item in our list. And if these do not line up, which is a very simple check to make for the computer, a very quick check, then we don't need to bother with a full comparison. Makes it a lot quicker, at least for some data types. Why do I hear error messages? Oh, that wasn't... okay, that was just my dog. Okay, that is interesting to know. My dog sounds like a Windows error. The hell? The acoustic is weird right now. Well, we can do the same in here. Compare the hash first, and only if it's the same hash do we actually bother with making a detailed comparison. And in here, well, it's already done. Technically, this contains will do the whole get hash once and do the comparison there. And then we do a second get hash in here for the item for potentially adding it. Doesn't really matter. Let's just ignore that for now. If we want to be really efficient, we could just make an internal contains method that expects the hash to be provided, and the public one just generates the hash and provides that along with the item, and the add method uses also the internal contains that gets provided with a hash, and we don't worry about that. That's not that big of a deal. Yeah, but there's one last optimization we can do here. And it's a bit complicated and maybe not worth it, but I should at least mention that. This part here. Right now, I have to make sure that every bucket is initialized with a negative value, with a -1. To make sure that when a bucket is used, the computer knows it's not 0, which is the default value, which would point to an actual index, which is valid, but that it's an invalid index. I can change the logic to skip this part if I assume that any index stored in a bucket, and in extension also items, because we copy the values to one another, if every index in there is actually the index in the array plus 1. What I mean is, bucket index, or if the bucket contains the value 0, it would mean index 0 in new items, or in items. Let's go maybe up here. A value of 0 in a bucket means index 0 in items, a valid list. But if I assume every value in here is the index plus 1, then I have to take the value from bucket, for example the 0, and then subtract 1 first, and that's the actual index. And if it's 0, that would be -1, which is invalid. So the default value that way in our array would already be invalid without me doing this. Of course, that means wherever you grab an index or work with the indices directly, you would always have to go -1, -1. Or if you do it assigning, you have to make a +1. So wherever you work with the indices, you might have to either decrease by 1 or add 1. And you have to decide if it's worth it for you to add that optimization, because if you have a couple thousand buckets or millions maybe, yeah, that will reduce the processing time. You have to do some additional arithmetic, adding, subtracting in between, but that's barely anything. That's pretty quick operation. The only thing that really suffers is the programmer, because you have to keep track of the different indices. Where do you have to add one? Where do you have to remove one? Do not get those crossed. So it makes programming harder, but for larger sets, it will make things more efficient. That's a trade-off. So I'm just leaving this for now because that's good enough for me. If you want to make it more efficient, you can drop this by assuming every index you store is actually the real index plus 1. So if you store an actual index, you have to add 1 before adding it to the array or storing it in the next. And whenever you read it, you have to subtract 1 to use it as an actual index, like here. That's a trade-off. One of the rare trade-offs for programmer convenience and efficiency. And now finally, let's talk about this part up here, the mathy part. I've mentioned collisions before, a couple of times now. We force the incredible amount of potential hash values inside an integer into a very limited subset of potential values for our buckets, because we have a limited amount of buckets. Ideally, we want to use the limited space we have to spread the values that come in mostly equally between different buckets. If we have only 10 potential buckets, we want to make sure that each one contains only a tenth of the total items we add. And we cannot really control that because we don't always know what kind of hash will be generated or how the hash will be generated. If you make your own classes, you can optimize them and create your own set, hash set, that deals with them, that is very much optimized around those specific subsets of potential hash codes. Great. If you can't do that, you have to rely on math a bit and statistics. If we assume that every item that comes in will have an equal chance for any hash code, there's still some math involved with just the size of your buckets. And this doubling up doesn't really lend itself to avoiding collisions. Again, that's the math part, and yeah, it's too far in my past. I don't know algebra that... Okay, that's not algebra. What was it? Malo? Mathematical logic? That might have been... I can't remember which one it was. University is so long ago. Anyway, for hash sets, we wouldn't double this up. In fact, we wouldn't just use random values for this. When increasing the size for a hash set, you would always prefer to have prime numbers. So if the old length isn't enough, you would create a new length that is sufficiently larger, that is maybe around twice the old size, that's fine, but it has to be a prime number. So let's, for fun, just in the end, private static and get x prime and number. So we're just making a very primitive brute force method to get the next prime that's larger than number. Not a good idea, just for fun right now. And how do we check for prime? We check if there's any number that's divisible. Or we check if it can be divided by any number. Oh god, I'm getting tired. So first, and candidate equals number. We're gonna assume that number might actually be a prime itself. So we include it in the check, candidate, and actually we're not limiting it. Candidate number, or maybe candidate less than number times 10. Let's set an upper limit. If it doesn't find anything in here, we're just gonna return the number itself. Candidate. So if we can't find any valid number, we just return candidate as is, or number. Upper limit, always a good idea, even though it's not the best one in this case. Just go with it. Should be large enough. And for int y equals, let's go for candidate -1. Actually, let's go with 2. I less than candidate plus I. If candidate divided by I equals 0, then candidate. Yeah, that's good enough. So for every candidate number, starting with the number itself, we're just checking if there's any number less than itself, but at least 2, that can divide it without any remainder. And then we return the candidate, because that's a prime then. And it's the next prime greater than our number. or equal to. Or if we can't find any one in the next 10x numbers, return number itself. So we're gonna use this, but as an argument. Get next prime, like so. And our code should still work just fine. True, 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 correct. False, false, true, that's also correct. That's true, false, false, correct. And b exists more than once. Everything works correctly. And the hash set is using primes now, even though that's not a good way to handle the primes. If you're curious, the official implementation for HashSet is just called HashSet. So just like dynamic array has a list, and queues and stacks exist in the runtime, HashSet is an official type that you have in the standard library. And they actually use something similar for very, very large primes. For the first, I don't know, many thousands of primes, they have a static array. Like, these are all pre-generated primes they store, and they just check in that existing internal array of potential primes for one that's big enough. So they actually did a lot of that processing beforehand. It's just a couple of extra numbers. Like, there are a couple of thousand of numbers, or at least a couple hundreds. Which sounds like a lot, but they're only integers, so it's not really taking all that much memory, and it speeds up the process by so much for almost any circumstances that you have with hash sets. Like, if that's not big enough, then I assume you're doing something wrong in your array, in your program. And I'm really feeling the 2 hours right now. I'm so not used to it. So we're not going to do the additional data structure. Not today. That's something we're going to look at the next time using just this code. Because there's another very special data structure that shares a lot of similarity with this one, but has its own very unique usage. Okay. Your homework. If you dare to, try to implement a hash set yourself. Your homework will be at least create a set, like the basic structure of I can add and remove and check if it's in there, and an item can only be in there once, and the order doesn't matter. Implement a set in any way you like. It can be a primitive one with an array or a list, or you can try a linked list. And if you're up for it, try to implement the hash part as well. You don't have to do it like me with a linked list internally inside an array. You can do it any way you like, but if you manage to create a set, try to upgrade it to a hash set in some way. And then as a bonus, you can try to just create a default class for linked list, which uses an internal array and manages that mostly efficiently. And bonus would be making a full hash set yourself with an internally stored array-based linked list. So, I'm gonna try to save my throat, because I have to work tomorrow and I have a couple of meetings I have to talk my way through. That's gonna be fun. Mondays have been really rough lately, because my throat is just destroyed. You cannot really hear too much of that, but trust me, in an hour I won't be able to speak anymore, I can feel it. So, yeah. That's it for today. See you next time.